Okay, my dear. It is 18th group. Nothing but noble gases. And boys, these are the elements present in the 18th vertical column of the periodic table. That is 18th group elements. What are those elements? That is helium, neon, argon, krypton, xenon, radon. These are the six elements present in the 18th vertical column of the periodic table. So that's why these elements are called 18th group elements. No doubt, the last element radon is the radioactive element. Radioactive element, last element. So because it is generally available from radioactive disintegration of elements, particularly radon. So that is, this is available from radioactive disintegration, nothing but radon. Radon during reduction, the disintegration gives, it is radium, gives radon. Okay. So a new element comes from radon, that is called radium. It is radium,
Yes.
that is called radon. So on that helium is also called helium H24. Radon is atomic number 80, my dear. 88. It is how much is the mass number? 88 and 26. It is 86 and 222. So why it is called as radon? Because it is coming from radium. That's why it is called as radon. Now, what are the elements? These are nothing but helium, neon, argon, krypton, xenon, radon. Now, all these are gases, my dear, first of all. All are gases. All are gases. This is the only group having all gaseous elements in your periodic table. All are gases. Now,
Okay, sir.
their atomic numbers. How these are? There is it is A2 atomic number 8. Sorry, add 8, 10, 18. After addition of 18, 36.
36.
So 8,
68.
8, 18. One
32.
more 18. 18
And
means 54. 32. Add 13. 80. How much? 32
6.
means
86.
86. 86. Yes, that is why it is 86. Okay. So these are the atomic numbers of the corresponding elements. Now
Yes.
the electronic configuration, outermost electronic configuration. So helium, it has 1s2 electronic configuration. 1s2. Boys, in this, the outermost electron with the differentiating electron entered into the s orbital. That's why it is s block element in your periodic table. Helium is s block element, but appears in p block element ending along with p block elements, but it should be an s block element. Next, neon, argon, krypton, xenon, radon. All these have general outermost electronic configuration as ns2np6n. So except helium, remaining elements have general outermost electronic configuration s2p6. That means outermost orbit have 8 electrons. It is called as octet configuration. That means all these elements have 8 electron configuration. That is why all these elements are very, very stable except helium. Helium outermost orbit and then 2 electrons. Is orbit, so not it should be unstable, is a double ending. It is doublet configuration. Now this one, both are doublet, duet. It is octet. Elements have 8 electrons, their outermost 8 are very stable. Okay. No doubt all these elements are very stable. Because of stability, these elements never react with any others. That is why these elements are considered as noble elements. That is inert elements. No doubt all these are gases. That is why these are called as noble gases. Sorry, inert gases. Other names are inert gases. Why these are called as inert gases? These are inert towards chemical reaction with others. So these gases are inert towards chemical reaction. Others, that's why these gases are called gases. Next, second one, another one, it is also called as noble gases. These are also called as noble gases. Why these are called as noble gases? So these have noble behavior, special behavior, ideal behavior. So that's why these are considered noble behavior. Almost
Okay.
these are not involved in the reaction with others, but except that is highly electronegative elements like oxygen and fluorine. Oxygen and fluorine may react with, no doubt not may, it is react with the last element, that is xenon and radon. So that means special case, in special way, xenon involved in the reaction with high electronegative elements like fluorine and oxygen. That behavior is called as noble behavior. So these gases are called as noble gases. Next, these are also called as rare gases. These are also called as rare gases. Why these are called as rare gases? Because these are available in our air in very rarely, very rare percentage. So that's why these gases are called as rare gases, available in air in rare percentage, rarely available. So these are called as rare gases. My dear boys, radon not exists in atmosphere, not exist in atmosphere except this, that is R8. So this is not available in air because it is available from the radioactive disintegration. That's why it is not available in air. So remaining five gases, what are those? Helium, neon, argon, krypton, xenon. These five gases only present in air. Which of the following noble gas not exist in air?
The radon.
Which of the following? So radon not exist in air and remaining five gases are available in air. Available in air. Next, what are the sources of these elements? So where these are available, no doubt these are present in air. That is why these gases are extracted from air, no doubt. So along that, these gases are also available in different situations. And those are, first of all, that is helium. Just a minute. Helium. So the basic source of this helium is natural gas. Available in USA and Canada. So available USA and Canada, and that is a natural gas which is available in USA and Canada. This is also existing. Okay, it is the commercial source of helium, and it is the commercial source. Commercial source helium is natural gas. Next, along that, helium and neon both are available in pitch blende. Pitch blende, its formula U3O8. It is uranium. There, helium and neon, rarely, very few amounts are available. Next, monazite sand. Monazite, and actually it is thorium ore. So far, it is. Next, clemite. Sorry, CLEVAI, clemite. So it is of uranium ore. So in these cases, helium and neon are rarely available. These are also some of the sources of helium and neon. Next, no doubt, helium, neon, argon, krypton, xenon. These are the five gases available in air. Among these five gases, argon is the most abundant gas. Argon is the most abundant gas in air. Very, very, very important. Among all these five gases, so the mostly available argon gas is argon, most available gas. Now, in air, what is the abundance of these gases? In air, abundance that is argon greater than, neon greater than, krypton greater than, helium greater than, xenon. It is by volume. Based on volume, this is the argon greater than, neon greater than, krypton greater than, helium greater than, xenon. It is based on volume. So based on mass, by weight, argon greater than, neon greater than, krypton greater than, xenon greater than, helium. It is by weight. It is by weight. So that means by weight, the least abundant gas in air is helium. But by volume, the least available gas is xenon, based on volume. Okay. So these are the very, very important
Yes, sir.
objective points towards your. So that is mains level and very, very, very important. So, but in both cases, the most abundant gas is argon. That is what I told just before. Okay. Next,
Okay, sir.
some properties about these gases. It is better to go with physical properties. Physical properties. What are these physical properties? First of all, boys, all these are gases, not? All are gases. All are gases. All are colorless, odorless, and tasteless gases. Colorless, odorless, tasteless gases. My dear, all these are monoatomic ending. Monoatomic, that means atomicity of these gases is equal to 1. That means helium exists only He. For example, hydrogen exists as H2. Oxygen O2, ozone O3, like that. Here atomicity is hydrogen atomicity 2, oxygen atomicity 2, here oxygen atomicity 3, but helium atomicity only 1. All these are monoatomic. Helium, neon, argon, krypton, xenon, all are monoatomic gases. Because these are monoatomic gases, the gamma value, that is Cp by Cv value, which is called as Poisson's ratio.
1.6. Okay.
Yes, Poisson's ratio, that is 1.66. Because these are monoatomic. Poisson's ratio 1.66. Okay, that is nothing but 5 by 3. Am I correct?
Yes, sir.
5 by 3. Yes. Cp by Cv ratio is 1.66. That is 5 by 3. So all these are monoatomic gases. Next. Next, diffuses through rubber. All are diffuses through rubber. Next, glass, rubber, glass, etc. Next, now atomic size. Atomic size. No doubt, in a group from top to bottom, atomic size increases. Automatically, ionization energy decreases. Okay, so atomic size increases, ionization energy decreases. So large difference in their atomic size are available. Large difference. Next, that is melting point, boiling point, and critical temperature, which is generally taken as TC. Okay, density, density. Next, all these are from top to bottom increases. Density top to bottom increases. Solubility in water. Solubility in water also increases. Solubility in water. Okay. So all those are from top to bottom increases. Okay. Now, my dear boys, boiling point. It is a special case. Boiling point of helium is 4.2 Kelvin. Boiling point of helium is 4.2 Kelvin. Very, very, very important. So actually, my dear boys, helium exists in two forms. In liquid state, there is helium gas exists in two phases. One is acts as helium 1 and other one is helium 2. Helium 1, helium 2. Okay, that is, it is at
Okay, sir. Sir, one.
1 atmosphere pressure. At 1 atmosphere pressure, so helium condenses as helium 1 and helium 2. And helium 1, it is no doubt it behaves like normal liquid, nothing but normal fluid. It behaves like normal fluid and its boiling point is 4.2 Kelvin, no doubt. Its boiling point 4.2 Kelvin. But helium 2 and this helium 2 exists at 2.2 Kelvin. Helium 2 exists at 2.2 Kelvin, but its behavior is behaves like a gas. Actually, it is liquid, my dear, but its behavior is similar to gas. That means it flows when, for example, no doubt helium 2 is a liquid. If we pour this helium 2 liquid, it's moving upward direction instead of downward direction, just like a gas. Okay, that behavior is considered as special behavior of the helium and so this is called as superfluid. So called as superfluid. Helium 2, where it is exists at 2.2 Kelvin.
0.2 Kelvin.
2.2 Kelvin, helium 2 gas exists, but its behavior is helium 2 liquid exists. Helium 2 liquid exists, but its behavior is similar to a gas. So it is called as superfluid. Superfluid. Okay. Next. These
Yes,
are
sir.
some general physical properties. Next. Electron affinity cases. Electron affinity. What is electron affinity, boys? So there is an atom. This is the nucleus of an atom. This is the atom. There is an electron outside this atom. If electron is entered into the outermost orbit, that electron is attracted by the nucleus. Because of attraction between this incoming electron and this nucleus, there should be some energy released. This released energy is called as electron affinity. So the amount of energy released when an electron is added to the outermost orbit of a gaseous neutral atom is called as electron affinity. So which is also called as electron gain enthalpy. There is energy released during electron gaining situation. So it is called as electron gain enthalpy. Electron gain enthalpy. Generally, energy release case because energy is released, the process is generally taken as enthalpy change. That is electron gain enthalpy. In general, negative because it is exothermic in most of the cases. But in case of helium, but in case of noble gases, so this electron gain enthalpy is positive. That is nothing but endothermic cases. Because all these already have unpaid, there is 8 electrons itself. These are not required any extra electron from outside. That is, these are not accepting any electron from outside. But we are we are thrown into the atom. So that's why, so they reject, but finally they can accept. Because of that, no doubt something energy will be some energy is required to accept that electron. That's why it is considered as higher electron gain enthalpy. It is a positive. Generally, electron affinity, electron gain enthalpies for any element is generally negative, but in case of noble gases, electron gain enthalpy is positive. That should be higher positive. So electron gain enthalpy values for noble gases is higher positive. Very, very, very important. That means, so more energy is required to add an electron to the in the orbits of the noble gas elements. Okay, so that's why it is higher electronic and enthalpy values. Those should be positive values. That means this should be endothermic situation. Endothermic situation. Okay, next. So noble gases have higher electron gain, higher positive electron gain enthalpies. Okay, their discovery and the just
Yes, sir.
behavior. See here. So what are those elements? Helium, neon, argon, krypton, xenon, radon. No doubt already I explained where radon is coming out. That is from radium. That is why the name radon is given to that because it is coming from radon. Okay. So now among these five elements, the first noble gas identified is helium in sun's atmosphere. In sun's atmosphere, the first noble gas is identified at the time of solar eclipse. So that's why helium is available from sun. Sun in Greek, because these are Greeks are discovered these gases. So in Greek letter, in Greek language, in Greek that is a culture, sun is nothing but Helios. Helios means sun. That's why it is available from Helios. That's why the gas is named as helium. So that means helium is nothing but Helios. Okay, nothing but sun. So sun's atmosphere, the noble gas which is identified, discovered in sun's atmosphere is the helium. Next, remaining gases. Among these gases, the first noble gas available is, that means these are all from air. Air contains these gases. Later, helium also available in air, no problem at all. So the second noble gas element identified is argon. So because it is almost non-reactive tendency, that's why it is a lazy element. Lazy, the word lazy in Greeks are considered argon, and that's why argon means laziness. Argon means laziness. First of all, argon
Yes.
is identified. Later, argon is the combination of three more elements. That means argon combination is the combination of three elements. So that means two more elements are hidden behind this argon. So that's why from argon, a new element is coming out. That's why that new element is neon. From argon, one more element is extracted. That new element is considered as neon. So neon means new. After that, a new element is identified, which is just hidden behind argon. That is a hidden, is nothing but krypton. Krypton is nothing but hidden. Later, a new element is discovered, which is a stranger for us. That we don't know anything. So that is why that element is called as stranger. The stranger element is considered as xenon. These are the some words why those names are coming out. So this is the theory behind that, the naming of those elements. Okay. So in sun's atmosphere, which one is the element available? Tell me.
Helium.
In helium. Next discovered element is argon. Argon means laziness, non-reactive
Argon.
tendency. Okay, from argon, that picture.
Neon.
So a new element is discovered. That is new element. That is nothing but neon. After discovery of neon, and one more element is extracted. That is hidden situation. So some new element is hidden behind argon and neon. That is considered krypton. At last, here argon, that is air contains a new element, unknown element. That is a stranger element. That is taken as xenon. So these are the names of, that is the names, how these elements names are available. That is the theory behind this. That is the theory behind this and naming of the elements. Okay. At last, helium also present in air. So therefore, helium, neon, argon, krypton, xenon are present in air. The only noble gas which is not available in air is a radon. The only noble gas which is not available in is radon. Okay. Next.
Yes, sir.
Now, these are some physical properties and some history behind noble gases. Let us discuss chemical properties. Shiva, did you understand?
Yes, sir.
Okay, now compounds of noble gases. Compounds of noble gases. So, different types of compounds available in noble gases. Compounds of noble gases. What is the first one? Hydrates. That means water molecules are attracted. So, particularly at 273 Kelvin temperature, that means how much is the temperature, my dear? In degrees centigrade?
0 degrees Celsius.
0 degrees.
So, yes, argon, krypton, xenon. Argon, krypton, xenon form hydrates with water. Like, so that is argon 6H2O. Hydrate means addition of water physically, not chemically. Next, krypton 6H2O, xenon 6H2O. Like compounds are available in it. These are nothing but hydrated compounds. Just like MgCl2 6H2O, it is hydrated magnesium chloride. Like this, here also possible. These are nothing but hydrated compounds. So first type of hydrated compounds are observed by your boys. Next, second one, coordination compounds. That means complex compounds can also be formed by our noble gas society. So particularly argon, my dear, I am taking argon. Argon has 4 lone pairs. So it is electron donating species. That is why this argon, no doubt, it is noble gas element. So it behaves like Lewis base. Electron pair donor. Lewis base. That means a Lewis acid electron deficient species like Lewis acid, like BF3. Boron trifluoride, there is an empty orbital in BF3 and E. So it is Lewis acid. So with this lone pair is donated to this one. That gives complex compounds. So that means different types of complex compounds. That means in this case, see here, argon with 1 BF3 compound is formed. Argon with 2 BF3 compound is formed. Next, argon with 3 BF3. This type of compounds. That means argon with NBF3 type complex compounds are formed. Argon with NBF3 type complex compounds are formed. So here argon to boron. There is a coordinate covalent bond. That type of complex compounds are formed. So that is in these cases, our noble gas element behaves like Lewis base. Lewis base. Next one.
Yes, sir. Lewis base. Okay.
Yes, these are all just physical treatments, but chemical reactions are also occurred, my dear. So now, chemical compounds. Chemical compounds from noble gases. So, my dear boys, actually noble gases have 8 electrons in their outermost orbit. 8 electrons in their outermost. That means they are not accepting any other electrons from outsides. That's why these are never involved in the reaction. So this is actually scientists feel up to first xenon compound is reported because these have high electron gain enthalpies, that two positive electron gain enthalpies, high ionization energies, very high ionization energies. So that means excitation of electrons are not possible almost all. So these are the theories actually scientists feel at the time. But a scientist, the name is Bertlet. Bertlet. So Bertletl. So he is the scientist. He reported first noble gas component, that is xenon component. What is that? Xenon hexafluoroplatinate. Xenon hexafluoroplatinate. My dear boys, here xenon has +1 charge, platinum, this PTF6 has -1 charge. So this is the first noble gas compound reported by Berkeley. That means xenon can also form compounds. So that means because this compound is formed, automatically xenon can involve in the chemical reactions. This is a complex component. So there xenon involved in the reactions. So that's why scientists feel like that. No problem, no doubt, no doubt. Xenon also can form complexes, can involve in the chemical reactions. So there's research going through that side because of this formation. That means the first noble gas compound reported by Berkeley, the compound is xenon hexafluoroplatinate. Xenon hexafluoroplatinate. Here xenon oxidation state is +1 and PTF6 has a -1 oxidation state. Okay. Next.
Okay,
Why, sir? Why Berkeley identified this one? Why? Because actually there is a known component. At that time is O2 PTF6. This is the known compound, my dear. What is the name of this compound? Oxygenide hexafluoroplatinate. Here O2 has +1 oxidation state. This one is just xenon is replaced with O2 molecule. So scientists identified that ionization energy of O2 is almost equal to the xenon. This is we know. Ionization energy of xenon is almost equal to O2 molecule. That is why. So no doubt O2 molecule can involve this type of compounds. Why not xenon is possible? Because both have almost same ionization energy. That means it is possible to remove the electron from xenon also. So that is why. So Berkeley worked like that side. Automatically he succeed and gives a compound XZPTF6. Okay. So that means it is exactly similar to this compound. Actually, we know this compound. Because this one exists, why not this compound exists? So no doubt, finally he succeeded, that compound exists, he feel, no doubt, he reported that compound also. Okay, na? Okay, na, my dear? So
yes,
why,
sir. Due to the
why? Here, the important point is, ionization energy of O2 molecule is almost equal to xenon. Okay, na? And also, PTF6 is the good oxidizing agent. That means O2 to O2 plus by the loss of electron. This is done by PTF6. Similarly, xenon is converted to Xg plus by the loss of electron. This is also done by PTF6. That means xenon is oxidized with the help of PTF6. That is why PTF6 is considered a good oxidizing agent. Because of that, this compound exists. After that, no doubt, scientists tried a variety of compounds with xenon because xenon ionization energy is less than that of remaining. Why not? Because see here, helium,
it decreases down
neon,
the
argon, krypton, xenon. Radon not exists actually, my dear boys. From top to bottom, atomic size increases, ionization energy decreases. That means least ionization energy is available for xenon. Least ionization energy available for xenon energy. So that's why xenon and somewhat krypton also involved in the chemical reactions with high electronegative elements like fluorine and oxygen. Okay, that means xenon with fluorine compounds are there, xenon with oxygen compounds are there, xenon with both oxygen and fluorine compounds are there. Similarly, krypton also. So that means we have compounds of xenon with fluorine, compounds of xenon with oxygen, compounds of xenon with fluorine and oxygen. Okay, let us discuss one by one. So, okay, did you understand, my dear? Why
yes,
xenon? Why xenon?
sir. Yes.
Can form compounds only with fluorine and oxygen? While
Because
xenon
of,
can form
sir, they
compounds,
have very high
yes,
electronegativity.
because of their high electronegativity values. Okay, because of high electronegativity of fluorine and oxygen, They involved in reaction with xenon. They can oxidize. They are good oxidizers.
Yes, sir.
Okay, they can oxidize xenon. Now compounds of xenon. Okay, xenon plus fluorine combination, the compounds are called as xenon fluorides. So here xenon with fluorine, XeF2 exists, XeF4 exists, XeF6 exists. These are nothing but xenon fluorides. Next, xenon with oxygen. Some compounds are available in it. Those are xenon oxides. Those are nothing but XeO3, XeO4. These are xenon oxides. Two types of compounds. Next, xenon with oxygen and fluorine, a new compounds are formed. These are nothing but xenon oxyfluorides. Oxyfluoride. Examples, some examples. XeOF2, XeOF4, XeO2F2, like that. These are nothing but xenon oxyfluorides. That means how many types of xenon compounds here we are going to discuss? Xenon fluorides, xenon oxides,
Three types.
xenon oxyfluorides. Three types of compounds. Let us discuss one by one. First of all, xenon fluorides. Xenon fluorides. What are those compounds? XeF2, XeF4, XeF6. Okay, so it is nothing but xenon difluoride. It is xenon tetrafluoride. This is xenon hexafluoride. XeF6, XeF4, XeO2. Now, how these are prepared? Preparation is just, my dear, when xenon reacts with fluorine. If xenon is in excess, that is, it is almost a 2:1 ratio, and that gives XeF6, X12, XeF. Okay, if it is, the ratio is when xenon with the fluorine, and the ratio 1:5, which is more now, fluorine or xenon?
Fluorine.
Fluorine. So by volume.
Yes, sir. Fluorine.
By volume. 1:5 ratio by volume. So under the catalyst, nickel, something else, that gives XeF4. XeF. For example, if xenon reacts with fluorine and the ratio 1:20, which is more. By
Sir,
volume.
fluorine is much more.
Yes, much more. By volume. It gives XeF6. XeF6. If xenon is in excess, XeF2 is the product. If fluorine is moderate, XeF4. So fluorine is much more higher, automatically that gives XeF6. XeF6. These are the preparation methods of these compounds. These are the preparation methods of compounds. Now let us discuss one by one. XeF2, XeF4. Before going to that, let us discuss structures of these compounds. So before going to the chemical reactions, let us discuss structure. These are very, very important towards your objective site. So let us, before going to discuss structure, now let us discuss about the electronic configuration and excited and ground state situations of xenon. So my dear, xenon, its atomic number Z is equal to 54. Its outermost electronic configuration is 5s2, 5p6, 5d0. 5s2, 5p6, 5d0. Now, 5s means it is a 5s orbital, it has two electrons. It is a 5p orbital. It has 6 electrons. And also 5d orbital. It is empty. It is the ground state electronic configuration of xenon. Okay. Now, if two fluorines are added, xenon should form 2 parts. Xenon with 2 fluorines, 2 bonds. That means xenon must contain 2 unpaired electrons to form 2 bonds. 2 unpaired electrons means it is the first excited. This electron is excited from here to here. How many unpaired electrons are there? How many unpaired electrons are there? 2 unpaired electrons. So that means whenever 2 unpaired electrons are there, their XeF2 is formed. Is this first excited state or ground state?
Sir, first excited.
First state.
First excited state. Now the hybridization is 1 s orbital, 3 p orbitals, 1 d orbital, sp3d hybridization. Okay.
Yes, sir.
It contains 3 lone pairs of electrons and 2 unpaired electrons. These 2 unpaired electrons can form bonds with fluorine. That gives these 2 are 2 bond pairs. That means here in this case, xenon has 3 lone pairs of electrons and 2 bond pairs of electrons. Total electron pairs is 5 pairs. So 5 means sp3d hybridization. Wherever sp3d hybridization exists, so the shape is actually the geometry of the structure is trigonal bipolar. Nothing but xenon is here. 3 are in the same plane. 1 above, 1 below. 1 above, 1 below. This is actually structure, possible structure, and trigonal bipyramidal. But
Yes,
3 lone pairs and 2 bond pairs. Those 3 lone pairs at the equivalent position. These are the equivalent positions. This is also equivalent position. And 2 fluorines above and below the plane. That means atoms are arranged just like this. That's why the molecule is linear. The shape of this molecule is linear, but actually the expected structure is trigonal bipyramidal, but the exact shape is linear. Therefore, finally, XeF2 molecule has linear shape with bond angle 180 degrees. Here, xenon is in sp3d hybridization. So, xenon has how many pairs? 3 lone pairs and 2 bond pairs. 3 lone pairs and 2 bond pairs in case of sp3
Yes, sir.
case. That is XeF2 case. So finally, tell me, buddy, what is the hybridization of xenon in XeF2?
sp3d.
sp3d.
sp3d. How many lone pairs is xenon?
3,
3 lone pairs. How many bond pairs?
2.
2. So in the entire molecule, how many lone pairs are there? So my dear boys, everywhere
actually,
fluorine has
plus-
3. Everywhere fluorine has 3.
Yeah. So
Here,
it will be
xenon also has 3.
9.
So how many total electron pairs? Total lone pairs of electrons?
9, sir.
9. So number of times he asked at the central atom or at the total molecule. If it is total molecule, number of lone pairs is 9. If it is at the central atom, number of lone pairs is 3. Please be conscious about the asking question. Okay.
Okay, sir.
So 2 bond pairs. This is about XeF2. So XeF2 is formed in the first excited state, there sp3d hybridization. Now let us discuss about XeF2. XeF4 means xenon, 4 fluorines, like this. That means how many bonds are formed by xenon here? How many bonds?
4.
1, 2, 3, 4. 4 bonds. That means xenon requires 4 unpaired electrons. But in first excited state, how many? 2 unpaired electrons.
Two, so
That's why you can excite 1 more electron. That is why from here to here. Now how many unpaired electrons?
4.
Now how many unpaired electrons? 4 unpaired electrons. These 4 unpaired electrons can form bonds with 4 fluorine atoms. Here the hybridization is like this, sp3d2 hybridization. Correct or wrong? Is this first excited state or second excited state?
Second acceleration, sir.
Second excited state. Now xenon has how many lone pairs? 2 lone pairs. These are the 2 lone pairs. So here xenon has 2 lone pairs, 4 bond pairs, total pair 6. Total pair 6 means sp3d2 hybridization. Because it is sp3d2 hybridization, actual expected one, that is structure is xenon, 4 fluorines, 4, it is a square pair are, one above, one below. It is nothing but octahedral sheet metal. This is expected, but we have only 4 fluorines, all those 4 fluorines at the equatorial position. Boys, those atoms within the
That will
plane
be,
are
sir, square
considered
planar.
equatorial position. Equatorial position.
Yes, sir.
Okay, above and below the positions are called as, this is above and this is below and those positions are called as axial positions. These are equatorial positions within the plane. So now these two positions are occupied by lone pair cell. This is one lone pair. This is another lone pair and two lone pairs. Now the shape is square planar. It is not octahedral. It is square planar. So structure is octahedral, but shape is square planar. What is the shape of xenon XeF4? What is the shape of XeF4?
So square planar.
Square planar. What is the structure of xenon XeF4?
Octahedral. Octahedral.
Octahedral.
Sir, shape
now-
is the apparent. Sir, shape is the apparent.
Shape is nothing but that is what we observe.
Okay, we have that is observed.
Observe one. So what you think
Theoretical
about
is
that?
octahedral.
Yes, theoretically, it is
So
a
that is called
theoretical one, it is
geometry.
actual one. It is a theoretical one, it is actual one. Okay.
Okay, okay, sir.
Okay. Now see here. In XeF4, how many planar atoms are there? How many planar atoms are there?
Five, sir.
5, sir.
Maximum 5 ending, because xenon and 4 fluorines are in the same plane. Total number of planar atoms are 5. Okay, lone pairs where they are located at the equatorial position or axial position.
So equatorial position.
That is where lone pairs are there. Lone pairs of xenon.
Oh, lone
Equatorial
pairs are
position.
axial.
Axial.
Sir.
Axial. Lone pairs are axial ending. Fluorines are at equatorial ending. Fluorines are equatorial ending. Okay now. Okay, now shape is a square
Yes,
planar. With bond angle, how much is the bond angle? 90 degrees, my dear. 90 degrees is the bond angle. It is about
Yes, sir.
XeF4. XeF4. Okay. Now, so here
Okay, sir.
hybridization is sp3d. Here hybridization is sp3d2. Now, XeF6, my dear. How many bonds we can form with fluorine? Total 6 fluorines are there. Each fluorine can form one bond. Total 6 bonds are required. 6 bonds means 6 unpaired electrons must be available in case of xenon. But already how many
Yes,
exists?
sir.
Only 4 exist. So that's why
We
one
need
more
to
pair
put
of electrons
third.
are going
Yes,
to be excited. It is a third excited state. That means how many unpaired electrons are there? In this case, 6 unpaired electrons. So because of 6 unpaired electrons, it is sp3d2 hybrid. Sorry, sp3d3 hybridization. It has one lone pair and 6 bond pairs. Correct or wrong? Total 7.
Yes, sir.
Correct, sir.
Total 7. One lone pair and 6 bond pairs. Total 7. And that is sp3d hybrid. sp3d3 hybridization. sp3d3 hybridization means there is a central atom. 5 are in the plane. Pentagon and one above and one below. Correct? So total 7. 5 within the plane and one above, one below. Xenon at the center. Xenon at the center. So now fluorine. Now one is, see my dear, one lone pair is also there. That one lone pair is at the equatorial position. One lone pair at the equatorial position. It is a fluorine. How many fluorines are there? How many fluorines are there? 6 are there?
6.
6. So, but because of lone pair, structure is not exact situation. Its structure is distorted. Distorted octahedral
Octahedral. Yes, sir.
or coped octahedral or coped octahedral. Whatever it is, mostly we are using like this.
Coped octahedral.
Pentagonal bipyramidal expected, but lone pair is at the axial position or equatorial position. Tell me, lone pair is at axial position or equatorial position?
Equatorial.
The
Equatorial
lone pair
position.
is
Lone pair is,
equatorial.
yes, lone pair is at equatorial position. Okay, so because of lone pair, some structure is deviated and finally leads to distorted octahedral end. Distorted octahedral, which is also called as coped octahedral.
Yes, sir.
Coped octahedral. Okay, so now, so here sp3d3 hybridization. sp3d3 hybridization. So sp3d, sp3d2, sp3d3. So in this case, so one lone pair and six bond pairs, my dear, at xenon. At xenon, one lone pair and six bond pairs are there. Correct or wrong? At xenon.
Correct.
Correct.
Yes, sir.
So her total electron pairs is 7. sp3d3 hybridization. Okay. Now let us discuss about the oxide. First of all, I am completing structures module. After that, some reactions. XeO3, XeO4. Let us observe, my dear. Whenever oxygen is involved in bond formation, there should be a double bond with oxygen. That means oxygen always can form two bonds. One should be sigma bond, one should be pi bond. So number of oxygens is equal to number of double bonds, my dear. For example, here XeO3 is there, xenon with three oxygens. That means three double bonds should be there. Correct or wrong?
Yes, sir.
Yes, sir. Correct.
Okay, that means xenon can form how many bonds? Total
6 bond.
6 bonds. When the 6
Oh,
bonds is possible,
yes. Third
first
excited.
state or second excited state or third excited state?
Third,
Third.
In third excited state, how many lone pairs of electrons are there?
6 lone pairs.
So one
Ah.
lone pair. Six
Lone pairs is one.
Oh, sorry. Yeah.
Lone pairs 1,
Lone pair one.
Bond
pair
Six
six.
bond pair.
6 bond pairs. That is lone pairs 1, bond pairs 6. Among these 6 pairs, 1 sigma bond, 1 pi bond. Correct? 1 sigma bond, 1 pi bond. 1 sigma bond, 1 pi bond. That means among these 6 bond pairs, 3 sigma bonds, 3 pi bonds. 3 sigma bonds and 3 pi bonds. Okay, now see here.
Yes, sir.
Yes, sir.
Xenon 5s2 5p3 excited state 5d3. It is the third excited state, my dear. Xenon third excited state. Okay, so that means, see, my dear, hybrid orbitals cannot form 5 bonds. Hybrid orbitals cannot form 5 bonds. So for the formation of 5 bonds, I left these 3 electrons for the formation of 5 bonds. So that means remaining electrons are only involved in the hybridization. That means sp3 hybridization exists. Okay, now what is the hybridization
Yes,
of
sir.
xenon? sp3. So that means this lone pair is here. These 3 unpaired electrons can form 3 sigma bonds. 3 sigma bonds. These 3 unpaired electrons can form 5 bonds. Okay, now?
Yes,
Did you
sir.
accept or not? Okay.
Yes, sir.
Now see here. From xenon side, d orbital. From oxygen side, p orbital is formed already. That is why this pi bond is nothing but p pi d pi bond. Correct or wrong?
Yeah. Yes, sir. Correct. Correct.
Okay. Shiva, please respond. Oxygen side, p orbital. Xenon
Yes, sir.
side, this d orbital is involved. So that's why the pi bond formed in XeO3 is p pi d pi. Correct or wrong?
Yes, sir.
Another pi bond also p pi d pi, like that. So second one involved. So another pi bond also p pi d pi. That means in XeO3, xenon has one lone pair. Every oxygen has two lone pairs. Always be conscious. Every oxygen has. Okay. So here sp3 hybridization, what we expected tetrahedral shape we expected, but one case is lone pair available. Because of that, the shape is pyramidal. Okay, now. So what is the shape of XZO3? What is the shape of XZO3?
Pyramidal.
Pyramidal. What is the structure of XZO3?
Sir,
Structure.
it is tetrahedral.
Structure is tetrahedral, but shape is pyramidal. Okay. So how many lone pairs exist at Xena?
One.
How many lone pairs? Xena?
One.
Only one. How many bond pairs?
3.
How many bond pairs?
So bond pair will be 6.
How many sigma bond pairs?
3.
How many pi bond pairs?
Also 3.
That means the number of p pi d pi bonds in XZO3.
Number of p pi d pi is 3.
3. All pi bonds are
P pi
here, my dear. So xenon has one lone pair, total 6 bond pairs. Among these 6 bond pairs, 3 sigma bond pairs, 3 pi bonds. All these 3 pi bonds are p pi d pi bonds. Okay. That means all these
Yes,
pi
sir.
bonds are identical or not? All these 3 pi bonds are identical or not?
They are identical. Yes.
Same. Okay. It is
Okay.
XZO3 structure. Its structure is tetrahedral, but shape is pyramidal. So here xenon is in third exilic state. Now, XZO4. How many oxygens are bonded here? How many oxygens are bonded here?
4.
4. So that means every oxygen can form how many bonds? 2 bonds. This is the 2. Every oxygen has 2 lone pairs. Now, see here. That means xenon can form how many bonds? Tell me. How many bonds can formed by xenon?
8.
8. That means 8 unpaired electrons required. Am I correct?
Yes, sir.
So that is why it is a 5s alcohol. It has 1 unpaired electron. 5p alcohol. It also has 3 unpaired electrons. 5d alcohols. It also has 4 unpaired electrons. What is the exilic state? First, second, third, or
Fourth.
fourth?
Fourth, sir.
Fourth exilic state. Fourth. How many unpaired electrons are here totally?
8.
8 unpaired electrons. But among these, 1 sigma, 1 pi. 1 sigma, 1 pi. 1 sigma, 1 pi. 1 sigma, 1 pi. That means total 4 sigma, 4 pi are there. Correct?
Yes, sir.
4 sigma, 4 pi. 5 bonds cannot formed by hybrid alcohols. That's why we left these 4 electrons, and these are only involved in hybridization. That should be sp3 hybridization.
Oh, okay.
Okay, because it is sp3, so structure we expect is tetrahedral. No doubt it seems to be tetrahedral. Correct or wrong?
Yes, sir.
Because no lone pair is there, no deviation there. No lone pair is there. All these are unpaired electrons, all these are converted into pi bond formation.
Yes, sir.
Okay, now. So no lone pair, there is no deviation. Therefore, the structure and shape. Structure and shape both are tetrahedral. Structure and shape both are tetrahedral. Okay, now see here, these pi bonds from xenon side and p are d are the from oxygen side p are the. So that's why this pi bond is p pi d pi bond. Correct or wrong?
Yeah, yes, sir. Correct.
So this is also like that. This is also like that. This is also like that. All those pi bonds are p pi d pi bonds. Now, how many p pi d pi bonds are here in XZO4? XZO4?
4.
Hmm?
4 p pi d pi bonds.
4 p pi d pi. How many p pi bonds are there?
So p pi
P pi bond.
0.
How many p pi? 0. How many d pi bonds are there?
0.
0. All the pi bonds in these cases is only p pi d pi bonds. Okay, now that
Okay,
means
sir.
one oxygen means 2 bonds. One fluoride has 1 bond. So like that, see. Now let us observe one more structure. You can identify XeO F4, my dear. XeO F4. How many oxygens are there?
There should be 5, sir.
How many oxygens are there?
Oh, oxygen 1.
One. One means two bonds, correct?
Yes, sir.
How many fluorines are there?
4.
Four. Four means
Four
four
bonds.
bonds.
So total 6
Nothing
bonds.
but total 6 bonds. Six
Yes.
bonds means 6 unpaired electrons are required, correct?
Yes, sir.
6 unpaired electrons. When is it possible in case of xenon?
Third
But
acceleration
when it is- Third acceleration. That means it is like here,
Yes,
correct?
yes. Yes, sir.
So now how many oxygens are there? One oxygen. No doubt. Xenon with oxygen, there should be a double bond. One sigma bond, one pi bond, correct?
Yes, sir.
So 4 fluorines, fluorine, 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 fluorine. So is there any pi bonds?
No, they are all sigma.
There are
But
sigma
it is
bonds. That means how many sigma bonds totally available?
5.
5. That means 1, 2, 3, 4, 5. These are involved in the hybridization.
sp3d2.
This is left for pi bond formation.
Yes, sir.
Okay. Therefore, sp3d2 hybridization.
Yes, sir.
sp3d2 hybridization. Okay. This pi bond is a p pi d pi bond. Okay, now sp3d2 is nothing but xenon. That is a square. One is above, one is below, and it is octahedral. Okay. So
Yes, sir.
xenon has one lone pair. That one lone pair is here. Okay.
Yes, sir.
This is a square. This is above and below. Actually, it is octahedral, but it is not a bond. It is a square and above one pyramid. And it is a square pyramidal structure.
Yes, sir. Due to
So
repulsion.
therefore, actual structure is actually we expect it is octahedral. Correct or wrong?
Yes, sir. Correct.
We expect it is octahedral, but it's what we observed is square pyramidal.
Pyramid.
So it is a shape. Structure is octahedral. Shiva,
So
okay now?
this
Okay, that pi bond is p pi d pi bond. Okay now? Next, let us observe. XeO2F2, my dear. Tell me, how many unpaired electrons required for xenon? Identify that.
4.
Huh?
Sorry, 6 are required.
So 2 oxygens means four bonds.
Yes, correct.
2
correct.
fluorines means 2 bonds. Overall 6. No doubt these are the 6.
Yeah, same, sir.
Okay now? But 2 oxygens are there. Xenon, 2 oxygens. It is a fluorine. It is a fluorine. This is oxygen. This is oxygen. Okay. So 2 fluorine. Now these are the this is the shape of the conditioning. Now how many pi bonds are here required?
one
How many
is
pi bonds?
2.
2 pi bonds. How many unpaired electrons are required? 6. So
6.
among them, four sigma bonds. 4 sigma bonds means P. Remove it. This is the hybridization case. What was this hybridization? sp3d hybridization.
sp3d.
sp3d. sp3d means what we expected. That is trigonal planar. One above, one below. Correct or not?
Yes, sir.
So that is a trigonal bipyramidal shape. But one lone pair is here, and 2 oxygens are here, 2 fluorines are here. The shape is called as a seesaw shape.
Seesaw.
Seesaw shape. What we expected trigonal bipyramidal, but the observed one is a seesaw. Therefore, structure is a trigonal bipyramidal. So that means this is the lone pair, my dear. This is a trigonal bipyramidal, but actual one is the seesaw shape. Actual one is the seesaw shape. Now, what is the shape of XeO2F2?
It was a seesaw shape.
Yes, the shape is seesaw shape. Next, structure is trigonal bipyramidal. Okay, na? Structure is trigonal bipyramidal. Shape is seesaw shape. How many pi bonds are here? 2 pi bonds. Both the pi bonds are p pi d pi bonds. Both the pi bonds are p pi d pi bonds. Correct or wrong?
Correct, sir.
Clear. So like this, you can design any structure. Like this, you can design any structure. So now next, our chapter is there is chemical bond. So in that chemical bond, so we will give a shortcut methods how to write these structures simplest way. Okay. After that, this is the shortest way. Okay, now Shiva.
Okay,
Yes,
sir.
sir.
Okay. Now let us discuss some chemical reactions of these compounds and there's some properties. Okay. Now
Okay.
let us start with xenon fluorides. Already preparation method I completed, my dear. So some properties, XeF12. It is colorless, transparent, crystalline solid. Are you writing?
Yes, sir.
Next, melting point. Its melting point is 129 degrees centigrade. Melting point is 129 degrees centigrade. Next, in this case, the most important reaction is hydrolysis of XeF1. Number of times asked, my dear. XeF2, when reacts with water, hydrolysis, that gives Xe plus HF plus O2 gas. Xe plus HF plus O2 gas. So see here, it is the gas. It is also gas. Okay. So O2, it is a paramagnetic in nature. Xenon, it is diamagnetic in nature. Both are the gases, but one is diamagnetic gas, another one is paramagnetic gas. So during hydrolysis of XeF2, so xenon, HF, and O2, you can balance this one. You can balance this one. This is 2 XeF2. That is totally 4. 2 H2O. 2 H2O means 4 HF. So it is balanced. 2 Xe. It is balanced. Hydrolysis of XeF2 is very, very, very important reaction. Okay. Next.
Yes, sir. Okay.
So when XeF2 reacts with oxygen, not oxygen, it is hydrogen because it is the oxidizing agent, my dear. Xe. That means it can oxidize hydrogen. That gives Xe plus HF. It reacts with I2. That gives Xe plus HI. Sorry. IF. IF, interhalogen component. Okay. When it reacts with HCl, that gives Xe plus HF plus Cl2. When it reacts with HI, gives Xe plus HF plus I2. In all these cases, XeF2 acts as oxidizing agent. In all these cases, XeF2 acts as oxidizing agent. Okay, now. Next.
Exists as oxidizing.
Oxidizing agent. That means H is oxidizing, H0 to H plus, I0 to I plus. Okay, now. Here hydrogen is removed, that is Cl minus 1 to 0, I minus 1 to 0. Oxidizing agent. So XeF2 is a good oxidizing agent.
Yes, sir.
Good oxidizing agent. Next. Next point. XeF2 forms additional compounds with metal halides, metal fluorides. Example, metal fluorides like NaF, Just a minute. D block metal fluorides, particularly niobium, NbF5, next TaF5, that is RuF5, ruthenium, like that. Osmium, OsF5. With these fluorides, XeF2 gives addition compounds. Addition compounds. Next, XeF2 with non-metal fluorides, like PF5, 15th group, ASF5, SBF5, okay, also gives addition compounds like this. See here, if XeF2 added with the PF5, this combination gives XeF plus ion, PF6 minus ion. That means ionic compound is formed by here. Here it is a cation, it is anion. So that means our xenon is available in cation. Xenon is available in cation, like this. Okay, this type of additional compounds are formed with non-metal fluorides. But in metal fluorides, just is normal case. Okay, now it is about XeF2.
So that is tantalum, that one, TAF5.
Yes, tantalum.
PF.
Now XeF4. Let us discuss about XeF4. Some chemical reactions towards XeF4. Before that, what are the physical state and certain conditions? It is white crystalline solid. White crystalline solid. Melting point is equal to 117.1 degrees centigrade. Less volatile than, volatile means evaporation. XeF6 acts as good oxidizing agent. Acts as good oxidizing agent. Okay. Here also hydrolysis reaction is very, very important, my dear. XeF4. When XeF4 reacts with water, hydrolysis gives Xe plus XeO3 important. It is a preparation of XeO3 also. XeO3 plus HF plus O2 and HF plus O2. That means two compounds are formed. Here xenon oxidation state 0, it is a gas. XeO3, that is XeO3. That is explosive compound, my dear. Explosive. Okay.
Okay, sir.
Explosive. So please be, you can balance that one. This is important. This is important. Okay. It is a complete hydrolysis. This is complete hydrolysis. If it is involved in partial hydrolysis, that gives when XeF4 reacts with H2O, that gives XeOF2 plus HF. XeOF2 plus HF. Okay. You can identify the structure of XeOF2. Its structure is a T shape, my dear. T shape. Okay, it is sp3 dehybridation. Xenon here it is sp3 dehybridation. Pi bond is there because of oxygen. That should be p pi d pi bond. Okay. Next.
Yes, sir.
when XeF4 reacts with, that is non-metal oxides like SbF5, that converts into XeF3 plus ion, SbF6 minus ion, just like XeF4, just like XeF. Okay. Some other reactions are there, but these are the
Okay,
very,
sir.
very important reactions towards XeF4. Now, let us discuss about XeF6. My dear, this is the preparation method of XeO3 also. Complete hydrolysis of xenon tetrafluoride gives XeO3. XeF6. XeF6. Now, it is a crystalline transparent solid. Crystalline transparent solid. Its vapors are in greenish yellow. Its vapors are greenish yellow color. Next, readily attacks glass and SiO2. There is nothing but SiO2 is one of the forms of glass. More volatile
Yes, sir.
than XeF2 and XeF6, F4. Next, strong chlorinating agents. That is fluorine supplying agent. Strong chlorinating agents. Okay. Now, some reactions here. See here, when XeF4 reacts with O2F2, my dear, that gives XeF6 plus O2. It is one of the preparation methods of XeF6. It is the preparation, most important preparation method, and that is why I am writing here. XeF6. Next, when XeF6 reacts with HF, okay, so it is a soluble, my dear, that gives XeF5 plus ion, HF2 minus ion H. Okay, it is ionic component. Ionic component is formed. Ions are there. So because of this, it is soluble in HF. XeF6 is soluble in HF because of formation of the ionic compound with HF. Okay. So next, hydrolysis reaction is also very, very important. Let us observe the hydrolysis reaction. Number of times asked, my dear. Hydrolysis reaction. See here, hydrolysis. When XeF6 is on hydrolysis, first of all, my dear, one oxygen is added, two chlorines are replaced. First gives XeOF4. Once again, if it is involved reacts with water, that gives XeO2F2, and one more water molecule is attacked, that gives XeO3. Along that, HF is the product. So that means XeOF4 and XeO2F2 are the partial hydrolysis products, and XeO3 is the complete hydrolysis product. Very, very, very important. Which are the following are the hydrolysis products of XeOF6? Means this one, this one, this one. These are the three hydrolysis products along with
Yes, sir.
HF. So complete hydrolysis of XeF6 gives XeO3. It is complete hydrolysis. These two are partial. hydrolysis products. So when XeF6 is a partially hydrolyzed, XeOF4 and XeO2F2 are the products. If XeF6 is completely hydrolyzed, XeO3 is the product. XeO3 is the product. Okay.
Yes, sir.
Next, this is very, 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 very important. Next one. When XeF6 reacts with arsenic fluoride, AsF5, AsF5, it is non-metal fluoride barrier. No doubt, just like that. One fluorine is here, X fluorine, that is XeF5 plus ion, and AsF6 minus ion. That is xenon available in cation cell. Okay, na? So here AsF5, BF3, and NaF, whatever it may be there. It is metal fluoride only. Metal fluoride also there. Similar way, similar. It is not Na, it is NOF. Just a minute, I am giving equations. See here, when XeF6 reacts with NaF, it is not NaF, it is NOF. Okay, that gives, it is 2 times XeF8 minus ion minus 2 ion and NO 2 times 2 plus ion. See here xenon is in anionic case. Here xenon is in anionic situation. Okay, these are some reactions towards XeF6. XeF6.
Yes, sir.
Now let us discuss about XeO3 and XeO4. Those are also important. XeO3 and XeO4. How to prepare XeO3?
Sir, by
Complete hydrolysis of XeF6.
Yes,
hydrolysis of
complete hydrolysis of XeF6, complete hydrolysis of XeF6, and also XeF4. Correct or wrong? In
Yes,
sir.
XeF4 hydrolysis, also XeO3 is the product. Correct?
Yes, sir, correct.
Okay, those are the preparation methods. Now, some chemical properties. So first of all, before that, physical properties. These physical properties are also important. So it is explosive solid. First of all, a xenon explosive solid is formed means there is nothing but XeO3. It is explosive solid, strong oxidizing agent. Okay. So non-volatile, white in color, soluble in aqueous solution. Okay, nothing but water. Soluble in water. And most important reactions towards Xe, when plutonium, boys, this is available in NCERT. This is available in your NCERT. When plutonium 3 plus ion reacts with XeO3 in the presence of acid, gives plutonium plus 4. That means Pu plus 3 is converted into Pu plus 4. That way here XeO3 acts as oxidizing agent. Pu plus 4, Xe plus H2O. Xe plus H2O. That is important reaction, my dear. Important reaction. And also, one more reaction. When XeO3 reacts with NaOH, aqueous NaOH, that gives Xe plus O2 plus Na4 XeO6. Sodium perxanate, name it. Sodium perxanate, the name of the compound. Sodium perxanate plus H2O. If this sodium perxenate reacts with HCl, that gives NaCl plus XeO3. Once again, XeO3 regenerated. Please be conscious. Plus H2O plus O2 plus O2. So sodium perxenate is the production. Okay. Sodium perxenate. So this is about XeO3. Next and last, XeO4. XeO4. Xenon tetrafluoride. It is yellow crystalline solid. It is yellow crystalline solid, not soluble in water. Not soluble in water. Preparation method. Barium perxenate, Ba2XeF6. Xanate means O6 and barium perxenate or sodium perxenate, Na4XeF6. Whatever it may be. Barium perxenate or the sodium perxenate when reacts with H2SO4 gives XeO4 O4 plus BaSO4, or if sodium perxenate is there, Na2SO4 plus H2O. XeO4 is the product. XeO4. Okay. That formed XeO4 on heating decomposes to Xe plus O2. Both are the gases. On heating decomposes to Xe and O2. Xe and O2. These are some chemical properties and some most important reactions towards xenon compounds. So, and in your textbook, some uses of xenon and noble gases are there. You can read very well. That is the end of our noble gases.
Okay, sir.